condition. So we go up here, we look. So we talked about boundary condition last week also. Okay. So not last week, on Tuesday, right? So one of boundary condition is when x is equal to 0, y is equal to 0. And on the other side, when x is equal to L, y is equal to what? 0. Okay. So from here, right? From here, we are going to apply when x is equal to y equal to 0. So from here, we realize that the constant b is equal to 0. Okay. Then we have boundary condition number 2. When x is equal to L, deflection is equal to 0. So we have this expression where y at distance L is equal to a sine PL is equal to 0. Okay. So now, from here, we have to find a condition where a sine PL will be equal to 0. Right? So this is a pure sine wave. So when this will be equal to 0, right, is where what? Is where sine PL or PL, right? PL is equal to 0, right? Or pi, 2 pi, right? So that's where the sine will be equal to 0, or 3 pi, 4 pi, right? Where sine, the whole expression, will be equal to 0. So when that's the case, PL is equal to, or P bracket L is equal to N pi, like what I've written earlier. Remember what I've written earlier? Pi, 2 pi, 3 pi, 4 pi. So we let PL is equal to N pi, where N can be equal to 1, 2, 3, or 4. Okay. So sine N pi is equal to 0. Okay. So from equation number 9, we realize that P, right? We realize that P is equal to N pi divided by L. Okay, so this is from equation number 9. Okay, now this is small p. This is not capital P. Okay, so this is small p. Capital P is the axial load. Okay, so note like what I told you guys before, where we have this expression, right? Where we have this expression where small p is equal to square root of capital P over EI. So where did this come from? Okay, just to quickly recap. So this comes from here, like what I highlighted earlier, right? This comes from this expression over here. And how we get to this relationship is because we relate what has been expressed from the elastic curve with the parent function. Okay, for parent function for what? For the homogeneous equation. Okay, so from here we equate equation number 9 and equation number 10. Right, so equation number 9, we have PL, or we have P is equal to N pi over L, and small p is equal to P. So what happened down here is we put this down here, right, and then we have this term down here, right. Then we rewrite the function where we have P over EI is equal to N squared pi squared over L squared. Okay, bear with me, we are almost done with the theory. Okay, so it's still very mathematically based. Okay, so from here the expression where P over EI is equal to N squared pi squared over L squared. So we have, then he come up with an expression, not him, or you just rearrange the equation where we have the critical load is equal to N squared pi squared over L squared EI. So this corresponds to the critical load. Okay, and then we can come up with a critical stress. We just divide by the what? A is the cross-sectional area. Okay, so we are going to focus on mode 1 deformation. Okay, we're not going to mode 2. Why mode 1? So mode 1, right, when it deforms in mode 1, it looks like this. So this is mode 1. Mode number 2, it will deform like this. right? So mode number 2. So this is mathematically, okay, in mathematics, okay? So if you look at, oh, sorry, I think I draw an extra. So it's 1, 2, right? So the structure will go into mode 1 first, okay? So it will go to mode 1, then it will go into mode 2, okay? So by the time in reality, what does it mean? When it hit mode 1, the structure will buckle already, okay? It will not be able to hit mode 2 at all, okay? So you can see structure. If I bring this half, okay, bring it to half, where I'm going to highlight, okay, right? So in reality, it will buckle in this pattern or the deformation pattern. It will not reach to this pattern at all. You will not see, you'll not see the bottom part at all, okay? You only will see mode 1, you not get to see mode 2, okay? So that's where we're going to focus on mode 1 deformation, okay? So you have this expression where equation 11, where you have the critical stress is equal to what? Pi squared EI L squared over A, okay? And then we are aware that I is equal to A R squared, okay? Where R, okay, is the radius of gyration. Can someone tell me what is radius of gyration, please? Can you all remember? It's okay, because I have not a clue physically what is radius of gyration. Okay, I'll tell you that. Physically, I have not a clue what is a radius of gyration at all. Really not a clue at all, okay? So but we know that I is equal to AR squared, okay? So when we substitute that formula, we have pi squared E, so we replace I with AR squared. So we substitute AR squared over here, right? You have L squared and A, and then finally, you have this expression over here. We have pi squared E divided by L squared over R squared. So from equation number 12, right, it's only valid for centric loading, okay, centric axial loading, right? So when we say it's centric axial loading, is the load is applied on the what? On the neutral axis. Okay, so what do I mean by centric? I'll express this again. So this equation that we have just applied, I'm going to draw a beam. Okay, this is our beam. One end is pin, and then I'm going to draw our neutral axis. So the green is our neutral axis, and then we have a load P X that's applied. Okay, so we have applied a load, and the load is, sorry, yeah, Px is because that is our x-axis. So this is applied on the neutral axis. Okay, so this is what we call centric loading. So what we have written down here will only work for centric loading. Okay, but then when our loading become this way. Okay, so same structure, neutral axis is still the same position, right? Okay, so this is our neutral axis. Now if we have another attachment by the side, right, we put a wrong color, sorry. If we have an attachment on the side, right, and then we have a load still applied in the x direction, this is eccentric loading. Okay, so equation number 12, for this case equation number 12 is not valid. Okay, equation number 12 is not. So it is only applicable for centric loading, right? So you'll probably learn eccentric loading in 3E05. Not probably. I'm very sure you'll learn this when you're doing your 3E05. Okay, but you need to know the background first. Okay. So now, using equation number 12, so we have derived an expression over here where we have critical load is equal to pi squared E L squared divided by R squared, right? So now we are going to let the allowable load to be 250, the Young's modulus to be 200. So we substitute it into equation number 12, and we come out with an L over R ratio, and the L over R ratio over here is known as the slenderness ratio. Okay, it's known as the slenderness ratio. So the slenderness ratio we calculate is 88.86. Okay. So what? What does this actually mean? Okay, what does this actually mean? So we plot a graph. Okay, so this is the graph we plot. Okay. So we plot a graph where the x-axis is equal to L over R. The y-axis is stress allowable. Okay. So from here, right, from here, we have calculated a slenderness ratio, a L over R ratio, to be 88.86. Okay. So what does this actually mean? If your slenderness ratio is less, okay, it's less than 88.8, it's on this side. So less, if L over R is less than 88.86, okay, the stress criteria that you have to design your structure is either force divided by area or deflection is equal to what? PL over AE. Okay. However, when you have when on the right hand side, if your structure, your L over R ratio is greater than 88.86, okay, you cannot design, or we cannot design our structure just based on stress divided by area or PL over AE anymore. You can't. You have to consider what? You have to consider buckling. If you don't consider buckling, your design is flawed. Okay, because if your L over R ratio, your slenderness ratio is greater than that, the structure will not hit the stress, but it will buckle. Okay, but it will buckle. So what we are trying to prevent is the onset of buckling. When will buckling initiate? And for this case, based on the stress and based on the stress, okay, based on the stress, okay, allowable stress, based on the Young's modulus, okay, we know what is the critical slenderness ratio. Okay, so we cannot apply P over A or anymore, or deflection is equal to PL over AE. Okay, you have to consider buckling. So when I say, some will say, hey, Eugene, what do you mean we have to consider buckling? You have to apply equation number 12. Okay, or you have to apply equation 12 or equation or this expression over here. Okay, this expression over here, where the critical load now is equal to pi squared, okay, n squared, or not, sorry, it's not, yeah, n over here will always be 1, okay, or pi squared over L squared multiplied by EI. Right. I think that's enough theory for now. Okay, there's some more theory to go for, but I'm going to section it out. Okay, I want to show you how simple it is. Okay, how simple it is to do this. Okay, it's not difficult at all. Okay, so let's do an example. Okay, so this is example number 1. So we have a beam over here that is 6 meters long. Young's modulus is at 200 gigapascal. The load P, so we are having a load P down here. So the load P is exactly acting on the z-axis that I have just drawn. and is moving at 16 times 10 to the power 3 Newton. Okay. Now the structure is pinned at both ends. Okay, so both ends are pinned. So what do we mean by